Okay, so here is what I did. I was convinced that the rate of flow was continuously decreasing, which of course makes things tricky. So I imagine what the graph would look like if at the 40-second mark, the rate of flow magically stopped decreasing. If that was to happen, the graph would stop curving and continue in a straight line in the exact same direction it was travelling at the 40-second instant. Does that make sense? But then how would I accurately calculate the gradient of that straight line, which I'm going to refer to as the 40-second rate line? Because I only know one point on that line, and to calculate the gradient of a straight line, I need 2 points. Well, I borrowed an idea from the second approach I showed you before. Consider the secant cutting at point A, 0, 0, and point B, 40, 3.2. As we already know, its gradient is greater than the gradient I require. However, if I change the position of the secant's leftmost intersection point, point A, watch what happens. Can you see the gradient of the secant seems to get closer to the gradient of the 40-second rate line? What a neat idea. In fact, if point A coincides with point B, I think we might have a single straight line, a tangent in fact, the gradient of which is a measure of R of 40. The instantaneous rate of flow at the 40-second mark. I have just one problem though. When point A is on point B, we are back to having just 1 point. And the gradient calculation, well, I guess it would look like this. 0 divided by 0. And that is a tough nut to crack. So for now, let's be happy to place point A very close to point B and calculate the gradient like this. So I could say the rate of flow at the 40-second instant will be a number close to 0.060005 litres per second. I'm not going to tackle how to calculate the exact value of the rate of flow at the 40-second instant just now. That's a dragon for another time. But 0.06 does look very compelling. So the key idea of the method I showed you is to use an average rate of flow over a very small time interval to approximate the instantaneous rate of flow at the end of that very small time interval. Or stated a bit differently, the gradient of a secant is used to approximate the gradient of a tangent. It's an age-old idea that leads to an important concept in mathematics called the derivative. Some calculators are programmed with a method of calculating the gradient of a tangent to a curve at a point, similar to the one I just showed you. In many cases, the value given is in fact the exact value of the instantaneous rate. For example, R of 0 is equal to 0.1 litres per second. R of 20 is 0.08. R of 40 is 0.06. R of 60 is 0.04. And R of 80 is equal to 0.02 litres per second. Do you notice anything? Look closely at those values. Do you see a pattern? Can you predict R of 100? What does that suggest about our gravity flow situation at the 100-second instant? In part 3, we will explore patterns similar to this one and see what we can learn from them. See you there.